Here we are once again. It is the Physics 190 video lecture. Physics 190 video lecture 3. So we're picking up where we left off last time. We had just differentiated complex functions and discovered something interesting. So differentiation of an analytic function. So let's start with that. So we have f prime of z df dz equals limit. So this is just the ordinary definition of the derivative, in fact. Except that this delta z here can approach 0 from anywhere and not just from two directions on an axis. And that has consequences. So limit f of z plus delta z minus z divided by delta z. So if this exists, then we say the function is differentiable. Now we were looking at complex functions. F of z equals u of xy plus iv of xy. Because a complex number has a real and imaginary part, and a complex function, right, which maps z onto the complex plane, can also be broken up into its real and imaginary parts as functions of these two variables, where z, of course, is x plus iy. Let's just write that for completeness. And then we find that if f prime of z exists, then we have what were called the Koshi-Riemann equations. So we have du dx is equal to dv dy, and du dy is equal to minus partial v with respect to x. Making sure I got that right. Did not get that right. So du dx, dv dx, I should make sure I copied this down correctly. dv dx minus du dy. dv dx minus du dy. Good, so those are the Cauchy-Riemann equations. And I think that's where we left off last time, and we did some definitions of different types of functions. These derivatives, we don't have to go into them too much. All of your standard functions that have well-behaved derivatives are unchanged. Okay, so the derivative of the sine of z is the cosine of z, your power laws, etc. They all work exactly the same. Square roots, fractional roots, logarithms, and things like that, where the functions are multi-valued, need a little more treatment. But generally speaking, your derivatives, all the rules that you already know, still hold true. Okay. So there are some really interesting consequences and powerful methods based on this fact here, just this derivative. You know, let me just give an example, in case I didn't do that last time. F of z is equal to a z to the nth power, nothing fancy here, n a z to the n minus 1, etc. So those rules are that simple for the most part. And we're now going to investigate these Cauchy-Riemann equations and some of their properties, and then some powerful techniques that we would encounter in fluid mechanics. So I'm going to do that. So today's lecture, I'm actually going to just dedicate to these equations and some interesting stuff we can do with them before we get back to the topic at hand. Okay, so let's talk about the Cauchy-Riemann equations. First of all, we have the following. So and let's write this down, Cauchy-Riemann equations or conditions. So let's do this. D squared u dx squared is partial d with respect to x and y. Okay. D squared u dy squared going to here is minus, I just bring the minus sign over there, is that d squared v dy dx. Well, if the mixed derivatives are the same here, and we always assume well-behaved functions, then if you add these two, you get 0. So d squared u x squared d squared u with respect to y equal to 0. So that is a solution of the two-dimensional Laplace's equation. And similarly, right, that follows immediately. If you do the same thing with v, you get d squared v dx squared plus del squared v dy squared equals 0. So that's a really important property. Really important property, and we'll showcase that. So functions that have this property are called harmonic, and when you have a pair of functions that do this in that form, they're called harmonic conjugates. So we can also write del squared, so in 2 dimensions, del squared u 0, del squared v equals 0. So the first important property. And u and v are called harmonic conjugates, so I'll write that down. U, v called harmonic conjugates. These are harmonic functions, 2 of them harmonic conjugates. So homework, actually trivial, but we're going to run with this in a couple of steps, so I'll just write this down. Prove that u of x, y equals 2x, 1 minus y is harmonic. Okay, you can prove that in the time it takes you to write it down. So the next thing we're going to do is show how to find the function v if we already know the function u. So that's also an important property. So what we're going to be given now is a function u of x and y, del squared u is equal to 0, and the Cauchy-Riemann equations. So the question is, if you have one of those, how can you find its harmonic conjugate? So next, given u, x, and y, del squared u is equal to 0, find its harmonic conjugate. And what we'll do is, so constructing v, by definition, v of x and y would be the integral dv dx dx plus dv dy dy, and we would just write x0 y0 xy. Okay, so what this is actually an expression written out of some integrals we talked about last semester, contour integrals in the plane. So when we did our little discussion of integral theorems, we would have written this v of r equals integral r gradient v dot, that's a v dot br along some curve, right? That would have been our shorthand that we used last semester, and when we were talking about integral theorems. And yeah, you just expand this out, you get your dv dx plus dv dy. That's the scalar product there, and that's the upper bound. Okay? But if we have it in this form, we can use the Cauchy-Riemann equations. So for the dv dx, do we have them down right now? Actually, no, we don't. Let's write them down so we have them here. So well, I'll just fill it in, and then they'll be there. So for the dv dx, we have minus du dy. dv dx. Is that right? Yes. Okay. So we have minus du dy, and then the dx, and then we have plus the dv dy, the du dx. And that would be the answer already. Okay, again, I'll just write the upper boundary up there, because now we took the function that we were given, u of x and y, and took u of x and y, and then integrated it up, and that's going to be the b. But we have to check for the path independence in order that this really be well defined. Is this a legitimate gradient, so to speak? Is this. So next, check path independence. Yeah, but if it works out, then this will be our answer, how to integrate up to get that unknown harmonic conjugate function. So yeah, to check the path independence, we'll make use of Stokes' theorem. So for Stokes, in 2 dimensions, we take the third dimension to be perpendicular to the xy plane. And so I'll write here Stokes theorem. So we have the curl of a vector field F, the surface bounded by a curve is equal to F dot dr in the closed curve. So closed curve boundary, I'll call it C, boundary of C, like that. Okay. Surface integral, if you want, like that. Curve, contour integral. So the question is, what would our f be? So in our example, that vector would be minus du dy, comma du dx, comma 0. Got our third dimension here. And the curl of this f would be d dx minus du dy minus d dy du dx. That would be the third component, right? The curl component that's perpendicular to the plane is one we want, and right? It's the one we want because this surface integral, okay, I'll draw a little picture in a moment. But yeah, this is clearly 0. You got this minus sign in both of them, so pull out the minus, you got actually, that is not quite right. dx. Oh, okay. Back up. Y to the x, x to the y here. Minus and minus. Equals 0. Third component of the curl. Okay, once more with feeling. It's going to be x squared with this one and a plus sign and y squared here. Okay, there we go. With the minus sign. So that's plus, negative times negative is plus, and that is just del squared u equals 0. Okay, pulled that out of the hat. So the curl is 0, and the integrals we were talking about here, here's my sketch. Now say we have x0, y0, xy. We're in the xy plane. And we take a path up to here, and for the path independence, take another one back again. Okay. So that would be this closed path here. And we wanted to prove that this closed path is always 0. And the curl with the surface integral is the left side of Stokes' law, and since the curl vanishes identically, then this is in fact path independent. So yes, we do have this now as our recipe for finding the harmonic conjugate. Okay. So then I will add, checking that I've got this u, y, x, u, x, y, good. So then I'll add to the homework, to that little homework problem. Find the harmonic conjugate. Now that we know that it's a reasonable definition and process, the antiderivative is there. So find the harmonic conjugate of this function up here of u equals 2x 1 minus y. And just to round it out, we can express that in a certain way. So right underneath here, f of z equals u of x and y plus iv of x and y. So from these found above, let's just go ahead and express this. Express f of z, in terms of z. So as a polynomial in z. Yeah, just in terms of z. Of z equals x plus iy. So yeah, you're going to have x plus iy type of terms in here, and you want to get, z plus z squared plus z cubed or whatever comes out there, okay? Kind of as a polynomial, in other words. As a small polynomial. squared plus cz cubed, whatever it takes to get that. Good, so that's a good little exercise in this. So now what we have is the Cauchy-Riemann equations. We have the property that del squared u, del squared v both equal 0, and that we can, given one, we can find the other. Okay, so now I have some properties that I want to go over. And then an example out of fluid mechanics. So first, the property that we're interested in is these, we call it orthogonal families of curves. So orthogonal families of curves. There is a property now that, suppose you've got these U and V or harmonic conjugates, then you can take U of x and y sub 1 of x equals c sub 1. And first I'm going to write this down, y sub 2 of x equals c sub 2. So these are constants, and what you do is you've got a function defined on the plane, and this, making this equal to a constant, asking the values that this takes equal to that constant, means that you've defined a curve, right? You've defined a curve in the plane, a curve in the xy plane. Okay. And ditto here. And so you could be here in the xy plane, and u of x1, y1 of x could be this family, okay, curves. So it'd be C1 takes on different values, okay, you get a family of curves here. And then v of x is a comma here, and y2 of x equals C2 would define another family of curves. So this one could be C2 taking on a value. And I've kind of drawn what a theorem states, namely that these curves, these families of curves, are orthogonal. So that's an important property of this function and its harmonic conjugate, is that these families of curves for constant values here are orthogonal. And we're going to prove that again using the Cauchy-Riemann equation. And this orthogonality will be apparent and play a role in our application. So it's a general property here. I've kind of indicated, again, C1 curves would be going this way here, and the C2 curves, different values would be this way. So I've drawn a picture that corresponds to the actual result that I haven't shown yet, but that I'm going to show. So we'll call this a theorem. Curves of constant u and v must be perpendicular to one another. So we'll put that as a statement. The curves of constant u, v are perpendicular to one another. And okay. So what we do is we differentiate all of those, or those two functions up there, with respect to x. first of all. So we differentiate with respect to x, and because it's a constant and a constant, the derivative with respect to x vanishes. Both of them do. So what we have, I'll just write differentiating. U and v. So the first one, partial u partial x plus partial u partial y partial y partial x, and I'll subscript 1 there just to tag it, equals 0, and dv dx plus dv dy dx sub 2, that's actually dy sub 2, so that's 2 there, equals 0. And what we're going to do is solve for the dy dx sub 1 and the second one as well. So dy dx 1 here is equal to minus du dx divided by du dy, and then the dy dx. Second set of curves, minus dv dx over dv dy. Okay, but now what we want to do is express these in terms of u. So we have minus negative du dy and dv dy du dx. And this is 1, so this is positive. I could skip, well, I won't skip steps. So let's just write this. So we have positive, we have du dx divided by du dy. And what this is, leave just enough room, this is minus 1 over dy dx sub 1, okay? Because it's just a minus, it's just lacking the minus sign to be like the inverse of that one. So, du dx sub 1 dy dx sub 1. So what we have here is the standard expression for perpendicular slopes. Okay, dy dx sub 2, 1 over, or negative of the inverse of dy dx sub 1. So that's the formula from just regular algebra, and that tells us that those slopes are related in that way, and therefore those are perpendicular lines. So good, we've got the perpendicular lines. So I'll just put that here. Two curves are orthogonal. Good, so that's what we wanted to prove right here. Okay, so we got the orthogonal families. That comes up in a couple of connections in the course of this subject. But now I'm going to give an example from fluid mechanics. Now for us this is kind of interesting because at the end of 105B, which we're also taking this semester, we intend to do a section on fluid mechanics. But I didn't intend to do this complex and that analytical discussion there, but we'll actually have it to draw on. So the following couple sections of notes here, you'll definitely be able to slot into your 105B lecture notes should we get that far. Good, yeah, let's see how much time we have to pull this off. Never have as much time as you want. Okay. We'll at least get this thing started. Because there's no point in rushing this now. So we just got these properties here. And I'll have to carefully state what what we're just accepting without proof from fluid mechanics. But these complex techniques are very powerful in two-dimensional physics. So in two-dimensional potential theory, in electricity and magnetism, and in two-dimensional fluid mechanics. So we'll talk about the fluid mechanics example. Okay, so example from fluid mechanics. Fluid mechanics. And here I want to be thorough so that you have something lasting. So what we're talking about is an ideal fluid, so an ideal incompressible two-dimensional fluid flow. And a picture to visualize is, suppose you've got an obstacle here and you've got a stream flowing past this obstacle. Okay, and you put a little dye in the stream and you'll get some streamlines like this. Okay. And they're not touching, okay. And tangent to a streamline, you'll have a velocity vector. So there's a velocity field in fluid mechanics, V, and this is what's called a stationary fluid, stationary flow. So it's not waving around or anything. This picture here, if you had these streamlines, would be static. Okay. So let's call this stationary flow around an obstacle. V equals the velocity vector field and then so we'll start there, and then we also have streamlines. And those are the lines where if you took all of these velocity vectors close enough together, okay, the fluid flow vectors. And conversely, if you just had the streamlines, then you could say, like field lines. Okay, you've seen that before. Field lines, like field lines. So you've got streamlines and velocity vector field. So now we're talking about an ideal incompressible two-dimensional fluid flow, and we can state some facts about it. It has what's called a velocity potential phi of x and y such that v is equal to the gradient of phi. So the field is the gradient of this so-called velocity potential, arrow. And it takes some doing to get to this statement, but we may even do that later on in 105p, but we're just going to take it as a given fact. It actually comes out of Euler's equations and some interesting stuff. But once you get there, you have this fact. So that's ideal and two-dimensional. The incompressibility of the flow, just think water is pretty incompressible. Incompressibility means that the divergence of this thing vanishes. So, all right, divergence of V equals 0, comma, because of the incompressibility. Okay? So that's what we're accepting from fluid mechanics. You've got an incompressible two-dimensional fluid flow, and ideal also comes in, and I'll say a word about that. Ideal means that there's no friction in it, and the boundary conditions are somewhat unphysical, but you know how it is with ideal systems. Okay, so ideal, no friction. So ideal incompressible two dimensions. Got this velocity potential, so V equals gradient of phi. Divergence of V is equal to 0, because that's what it means to be incompressible, no sources. Okay. Yeah, so what follows from that immediately is del squared phi is equal to 0. It follows del squared phi is equal to 0. Okay, we'll send this up. Okay, the next thing I'm going to talk about is the streamlines, which I've defined there and given a picture of. So we want to characterize the streamlines mathematically. And the streamlines are characterized by in fact, you just put that in an XY plane, and since the vector is tangent to the streamline, we can say dy dx, the slope of a streamline is equal to v sub y divided by v sub x, the two components of that vector. Right? That's immediately apparent there. V has components v sub y and v sub x, and that's the slope, dy dx at that point. So we can also write that as vx dy, I'll do this, minus vx dy plus vy dx equals 0. Okay. So that's immediate characterization. Okay, fine. So now we want to construct a stream function to describe the streamlines. So to obtain a stream function C of x and y, we want C of x and y equals constant to describe a streamline. So I'm going to write that down that way. Yeah. So to obtain a stream function, see if I can find that is constant along a streamline, we can just construct that. We'll say that dc is equal to 0 because it's constant along the streamline, so it's differential along the streamline is equal to 0, or dc dx dx plus dc dy is equal to 0. So let me put the minus sign in the right place. Dy dx dx dy. I think in my notes, like that. So yeah, we're going to compare the two. So if we compare this and this, let's go ahead and give each one a star, and double star. Then we will have, for the dx, we'll have minus dx is equal to dx minus dy is equal to deep C dx, and dx is equal to deep C dy. Make sure I chose these right. Now these are obtained from the gradient of phi. Okay, so comma, but dx is equal to d phi dx, comma, dy is equal to d phi dy. So let's see what happens when we put that together. I'll use this space right here at the left end of the board. So what we get is d phi dx is equal to deep C dy. Phi dx is equal to deep C dy, and the other one, d C dx is equal to d phi dy. So let's put a box around those. Make sure we got them right. Yes. Okay, so let's hold on to these, because these are just the Cauchy-Schwarz relations once again, in a very unexpected place, because we haven't done anything with complex numbers yet. Okay, but we have obtained the Cauchy-Schwarz relations. Cauchy-Schwarz. And so now we can draw a really interesting conclusion. Yeah, okay. So let's put together what we have here. Because by construction, phi was already harmonic, and C is going to be harmonic in the same way that we had it before. So I want to formulate, that picture would be good. Okay, we'll leave it right there. So I want to formulate this. Checking the time. Oh, yeah, we got this. Okay, so let's put this down systematically now. So we have the Cauchy-Schwarz equations. As before, del squared phi is equal to 0, del squared C is equal to 0. Okay, got the Cauchy-Schwarz equations. So next, ideal flow is tangent at a surface. Or tangent to a solid surface. You know, at the surface, that is to say, you know, you've got a solid surface here, and fluid flow, you can't have a normal component at the surface. Okay? You can't have a normal component, that's where the velocity stops. Okay? So that means that v dot n hat equals 0 at a solid, surface, B dot n hat is equal to 0 at a solid surface. Okay. Or B sub n. You could say B sub n. Yeah, I don't want to. Okay, yeah, that's why we're not using U and B anyways. Okay, B sub n equals 0 at a solid surface. Okay. So that means, since it's just the tangent component, that we're going to have C being equal to 0 or equal to constant along that streamline at the surface. So let's write that down. This means the profile contour of a surface must be equal to 0, must be a streamline. The surface is a streamline. In other words, our stream function takes on a certain value of a constant at one of these surfaces, and if it's a constant, we can let the constant be equal to 0. So this means C equals constant. If you want, you can choose the constant equals 0 at a surface. Okay, and so now we're ready to pull all of this together. And I may run over on this one, then I'll make the next one shorter. Let's see, we can't go through this. So here's what I'll draw. Well, actually, I'll end this with this conclusion here, and we'll do the calculation next time. We'll do the examples next time. So summarizing what we have up here, I'll kind of put this as a theorem. So we'll write it this way. Since an analytic function f since an analytic function f of z equals phi plus ic has phi c that satisfy Koshi-Riemann, and Laplace equations, we can conclude f of z equals phi plus I times c that takes on real values at a boundary i.e. what it means for this function to take on real values is that this imaginary part vanishes. So if you have a function where this function c vanishes at the boundary, equals 0 at the boundary, c equals 0 at the boundary, now we can conclude if then f of z is the solution to a fluid flow problem. Solution to a fluid flow problem. So I think this is sufficiently thoroughly formulated. So if you put this down, space it out right, make sure you see the logic of this. You know, I'm tempted to keep going here, even though this is going to be a slightly longer operation. You know, maybe I'll go an hour this time, another 10 minutes, just to wrap this up. So the point is this. This function here, with all of these properties on the right side, it just has to be a differentiable function, and then it is automatically the solution to a fluid flow problem. A solution that could, under other circumstances, be enormously difficult to find. There's a bit of backwards engineering in this, because since it's any differentiable function, you just put one in here and it is the solution to a fluid flow problem. What that problem is, you don't know yet, okay? You can kind of work backwards. Okay, so you know what? I am going to just extend this lecture and do the example, because now we've just constructed everything that we need. Remember, a function c of x and y, same with phi, but this function c of x and y equals constant, that defines a curve, right? Because it's a function of two variables equals constant, it implies a y of x. So that's why the constancy of this, and it can equal 0 as well, that's a constant, implies a curve. And that curve is the boundary to your fluid problem. So I'm going to go ahead and do the examples after all. Yeah, I'm going back and forth on this. Back on forth on whether to do this. Let's just do this example. This is a great example. Okay, so here's our XY plane. And we're going to just block off everything, so we're just looking at the first quadrant. Okay. And we can imagine a fluid flow kind of sweeping in from above. Right, it can't actually hit the corner, but sweeping through here. So this is the corner of a giant tank or something, or just a corner where a fluid flow is able to come from above and exit down to the right. Okay, so what we're going to do is look at f of z, a very simple function, a times z squared. Okay, so what is a times z squared? A times x plus iy, the quantity squared, a times x squared, when you square this, 2x iy, and then minus y squared. So x squared minus y squared, and you have plus a plus I times 2a xy. Okay. So what we're looking at here, this is our phi of x and y, and this here is our c of x and y. So where does this function take on values of equal to 0? Well, it takes on values equal to 0 right here. So f of z equals some constant times z squared is actually the function for this fluid flow. Of course, if I hadn't known this, it might have taken a while to find it, but I'll tell you later how you can extend these ideas a little more, okay? So yeah, when x is equal to 0, we're here. When y is equal to 0, we're here. So that is satisfying these boundary conditions. That means that you're going to get the v sub x and v sub y out of this function here. And these curves you're going to get right there. Okay. Streamlines here. And that's, you know, I drew these streamlines. So let's look at this. Streamlines C of x and y equals constant. Okay. So since we have 2axy equals c, we have y equals c over 2a 1 over x. Okay, so the 1 over x function is what I just drew there to begin with. Right? So yeah, I knew that answer. Okay, and what about velocity field? V equals gradient of phi, so v sub x is equal to 2ax, v sub y is equal to minus 2ay. So it's xy. If you take that vector and make the y component negative, you get those vectors like that. So that comes out. Now I wanted to extend this for you guys, and that's what we'll play around with next time. Here's what I'll do. I'll formulate a homework, and basically I've done the homework. So for this problem, homework. So for this problem right here, 1, find v, right? I've just done that right there. 2, sketch the streamlines. 3, show that del squared phi equals 0, del squared c equals 0. Of course, that'll be trivial. 4, show that v dot n hat equals 0. So v dot surface normal equals 0 at the boundary. And I'll finally write down what we're going to do next time. Yeah, go ahead and put all these notes together so you really see them clearly. All the ingredients are there. And then I'm going to add something that we'll talk about next time to round out this discussion. In fact, yeah, we'll just formulate the whole problem next time. So we now know what f of z equals a z squared means. What about f of z equals a z to the nth power n equals 1, 2, 3, 4, and so on? What do they mean? Okay. Turns out that we can extract their meaning based on what we've done here, and that'll be a good place to leave the discussion of the Koshi Riemann, the complex methods. I may come up with a little more, but this is a really nice section. And when we get to fluid mechanics, possibly we'll actually derive those statements about gradient and so forth. And then we would have a nice, complete presentation there on that subject. Okay, good. This went longer than we wanted. We'll do the next one shorter. No problem. An hour, not so bad. Okie doke. See you guys next time.